Elasticity, the physics of springs. Uh, it's really two equations. That's it. That's all. Two equations. Not like circular motion where there were what? 10 different terms? 9 different terms? 9 different terms. So elasticity is pretty darn straightforward. Hopefully you will find it the same as well. This can be a gimme. You are welcome. Let's see if it is a gimme. Here's half of the equations to learn. The force exerted by a spring can be modeled using Hooke's law. Notice model. Hey, have I even talked to you about what I mean when I say model? No? Okay, just when we talked about tension versus springs, I said springs we'll do later. Tension is a spring that doesn't stretch. Springs are a spring that does stretch. Which is a given object? Well, it matters what we are representing. There is no fundamental quantum mechanical particle called the spring particle versus the string particle. These are all different ways of representing different features about the world. No physics equation is the universe. Different physics equations represent parts of the universe. This is the nature of physics. A model is how we are analyzing something. It is not the thing itself. So, when I say the force can be modeled using Hooke's law, well, that depends on what degree of precision you're doing it. You will find it useful in next slide, I think, next slide, to start by analyzing without Hooke's law at all. You can simply say the force that a spring at equilibrium, a spring that is holding an object, you can ignore the fact that it's a spring completely and say that the upward force must balance mg. If the object it is holding is at rest, a fish on a fish scale must experience an upward force equal to its weight. Otherwise, well, it's not going to be staying there for very long. However, if we want to understand how far the fish scale stretches down, the vegetable scale, whatever springs down, then using a tension model isn't very useful. So. Hooke's law says the force that a spring exerts, and I ran out of letters, so I just say Fs, is equal to K, which is a constant called, you'll never believe this, the spring constant, times the change in length. Delta X vector means the change in the length of the spring. Okay, now, these letters. K is called the spring constant. The constant that describes the spring is the spring constant. Yeah, big stretch there. Big stretch. Oh, that could be a pun. I didn't see that one. Big stretch. I'll work on it and come back to you next week. I'll tell you the pun later. I want to emphasize something about the spring. K is different for each spring, but if you stretch or compress the spring, K does not change. So if I have a spring and you have a spring, we might have different springs. We might have different spring constants, or might have the same, but the spring constant depends on the individual spring. As you stretch and expand and compress the spring, K stays the same for any given problem. So if you know that you are not changing the spring, you could find K once and then keep using it. If I say you replace a spring with another spring, then you cannot assume that K is the same. Delta X here, delta X measures the compression or extension in the spring. I'm going to say the change in length of the spring. Please think about this. It is not uncommon for students to say Kx and then plug in absurdities. For instance, if I've got a 10 centimeter spring, which is currently 10 centimeters long, do you think it's exerting a force of K times 10? If you've got a spring that's 10 centimeters long at equilibrium when unstretched, and it's currently 10 centimeters long, that means it's not stretched at all. So the extension of the spring is very important. It's the current length minus the unstretched length. Do not plug in the length of the spring. It is the change in length, the extension or compression. By convention, a positive delta X means that we are longer than the original spring length is. It is expanded. The minus sign here says that if x is in the expanding direction, if a positive x is the expanding direction, negative expansion points which way? The spring is trying to exert a force that compresses itself, yeah? Negative expansion equals compression, negative compression equals expansion. I don't know if we're talking about up, down, left, right, in, out, northeast, southwest, whatever. But whatever the direction of delta x is, force is in the opposite direction. That also should be a pretty darn common sense idea. If you stretch a spring, it tries to compress itself. If you compress a spring, it tries to extend itself, yeah? Watch out! When I give you a problem, this minus sign, I want you to know, I want you to write down, I want you to memorize this minus sign, but I want you to think about its meaning. A common goof is for students to plug in this minus sign everywhere, even where it does not apply. The minus sign shows us the direction of the force. If you know a spring is stretched beyond its equilibrium length, you could just plug in that the direction is, say, if I've got a string stretched downward, I could just plug in that it's going to pull upward and use positive kx. The magnitude of the force is kx. The minus sign simply tells us that the force is in the opposite of the direction of the stretch. Stretch compresses, compression stretches, tries to expand. Don't just plug in minus signs because the equation has a minus sign. Yeah? Okay, so K is a constant that depends on the individual spring. We'll show how to measure it, blah, 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 blah. Delta X is the extension compression of the spring measured in meters. I mean, how do you measure an extension or compression? A change in length, that's meters. I want to emphasize also here, this picture I'm bringing up here, your ballpoint pen spring or whatever, you guys see the spring inside a ballpoint pen? Those sometimes have the links touching. Can you compress those? I mean, if you're really strong. What I want you to have in your mind, a default picture for a spring is more like this: car shocks or the expanded springs. Sometimes in a clicky, those pens, ballpoint pen. Sometimes they'll have springs that look like this. The point is, I don't want you just to think of a spring where all the links are touching. A slinky can be expanded but not compressed very well, right? That's not your, I don't want you to think of a slinky as your default picture. Think of a spring where the links aren't touching. You can compress this, you can extend this. Whichever direction you push, the spring pulls in the opposite direction. Okay? A spring is not just a slinky. Yes?
What about a spring that doesn't compress after you pull it?
Very good point. A model is a smaller representation of a thing which captures some of its behavior, but although my brother built many model airplanes, very few of them flew dogfights and shot each other down. Model represents some of the world around us. Any real spring will have a length beyond which it does not return to its original shape. You stretch out the spring. That's not included in this equation. Just like, for instance, weight equals mg, yeah? M times a constant. Well, if you go to the moon, you don't still have g equals 9.8. G depends on where you are. Anywhere on the surface of the Earth, you could just plug in g equals 9.8. What I said in class is, unless I specifically talk about outer space, you can assume g is 9.8. Well, likewise, that is representing some of the universe, but just saying constant 9.8 is not representing all of it. This represents when a spring is in its so-called elastic region. The elastic region is when a spring will return to its original size and shape. As long as you're stretching, not overstretching or overcompressing the spring in the so-called elastic region, it will be very, very close to this law. Did y'all hear his question, by the way? He asked, what about if you, wait, how did you word it? I want to represent, say again.
What, so how would you,
When the spring stretches out?
yes,
Is that what you said?
what would you have?
So the region, the how far you can stretch it before it stretches out. Um, One, I don't know for sure, but I'm pretty sure that is tabulated elsewhere. That is, I think that it's called like the ultimate strength or the tensile strength or the ultimate shear something, something, something. That is known, but I don't know it. I'll show you a graph later on that shows this point. Actually, it might even be labeled. What I'm going to test you on, what we're going to need for this course and going into next semester as well, is to represent the limited range, the range limited by where you're not breaking or damaging the spring. You want to go deeper into stuff? Absolutely. There's and for that matter, what are you gonna be a doctor? What's your career plan? Okay, so in the medical profession, as I will say on the very next slide, lots of things are springs, and you care very much when materials do not return to their original size and shape. Okay, so that leads into what is a spring? Anything's a spring, sort of. The spring model applies to a butt ton of different cases, not just coils of metal. For instance, if I have a coil of metal, well, sure, that's a spring. A guitar string, which keeps a constant length no matter what you do to it, wouldn't vibrate. If it kept a truly constant length, you try to pluck it and nothing could possibly happen. For a guitar, for any string instrument at all, to have music made out of it, there's got to be some stretch and then return to its original position in vibration. Hell, not just any string instrument, any instrument I can think of has this to some extent. My trumpet, when I was in high school, when I played the trumpet itself vibrated. The metal itself was deforming one way, then the other, then the one way, then the other. A very tiny millimeter amount of change, probably less than a millimeter amount of change in the metal size, but it's still vibrating. That can be represented as a spring. Rubber bands, well, that's kind of duh. Although I will point out that rubber bands, that's only the stretchy direction, right? Rubber bands don't really oppose when you try to compress them, they just fold. A table is a spring. If you look very carefully, you know what, maybe I should not, what the hell? Okay, if you look very carefully at the surface of this table, don't tell my wife. The surface of the table is going up and down a little. Just a little. But the more I press on it, you want to come up here too? You want to climb up here too? The more you press on it, you know what? Liability, actually, I shouldn't do that. Risking my neck is one thing, risking a student's neck. You guys pay tuition, I take the money. Arizona Board of Regents looks rather harder on you guys getting hurt. Okay, so the point is, the more weight you put on the table, the more it deflects. Then you put more and more and more weight on the table, and eventually it breaks. And that's exactly what we were talking about a second ago. Eventually you reach a breaking limit, a place, a force that the spring can't return from, a maximum sort of strength, which is actually sophisticated to the point that I don't remember it. Okay, so tables are springs. Bones are springs. If you measure very carefully, if you push on an arm or pull on an arm a little bit, not just the joints, but the bone material itself is very slightly rubbery. Unless you're Harry Potter in book 2, in which case it is very rubbery. No Potterheads? Okay, whatever. Bones can be represented as what's it? And in fact, if I recall correctly, this is also an old memory, but if I recall correctly, there's actually a medical test that ends up measuring something about bone health based on its elasticity. And no, they don't actually just take the patient and stretch them back and compress them, at least not very much. I think they do something a little bit more sophisticated than stretching them until they break, but I don't know. I'm not that kind of doctor. The point is, the spring model can apply to lots of things. You can always take the spring model and say as the first approximation for all sorts of materials. And then if you want to be more sophisticated, you could say, all right, this is only springy if you stretch and compress it by 1 millimeter. Well, this acts like a spring even if I stretch and compress it by 10 centimeters. Well, this acts like a spring if I stretch and compress it by 1 atom's width. Okay, so when do I want to model something as a spring? When don't I? It depends on the material. It depends on what you're doing, what you care about. Springs, they can be anywhere. And next semester, we're going to model a whole butt ton of things, talking about them as this is effectively a spring, and the effective spring constant is blah, 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 blah. That all goes back to here. Okay, now let's do a problem. I've got problems, so do you. Google question A. Take a stab at this. You check your numbers, case mass. You're real close. Hmm. Excuse me. Hey, you should also, I encourage you to do a sanity check here. Sanity check, a good sanity check might be, I'm pulling harder on the spring. Does it make sense that it stretches shorter? The springs pull harder or when they go longer or shorter when they go longer? Also, I've got a number of people blindly plugging in negative signs. I have to think about what the negative sign means, my dudes. Also, I've got a couple of people telling me forces. I didn't ask for forces. Turn to your neighbor and discuss real fast. We've got a lot of correct answers, but not enough.
I was thinking about the radiant on Twitch.
Alrighty-o. As many people correctly deduced, when I say is hung from it, properly I should have said hung from it at rest, because if the block is bouncing up and down, things get very complicated indeed. But without any other information, you can assume, or if you ask, I will say, no, it's just hanging there. It's just at rest, stationary. So weight downward had better darn well balance kx upward. Why not negative? If the spring is being extended, I'm describing it's being stretched, it's trying to recompress. The compressive direction is up. I'm already incorporating the fact that up spring and down weight are opposite directions when I set them equal, yeah? So I set weight equal to spring force. If it's just, as I said, just sitting there, mg equals kx. Solve for k, pluggy chuggy. Note g cancels out here. If I had to do many of these equations, it would, if I were doing this multiple times, it would be efficient to rewrite this in a slightly different form. If you got 11 centimeters, good, great. Here's a trick. If you know that the mass times g divided by the stretch is a constant, then if you know that you're never going to change the spring, if I give you a series of questions, perhaps on a midterm, for instance, or a final, if I give you, hint, hint, if I give you a series of questions, it may be useful to say that mg over stretch 1 equals m2 g2. Wait, hold on, g doesn't change. G1 equals G2 equals whatever, so I could just cancel it out. So the mass, in this case, the mass to stretch ratio is the same. So take a look at this. I could just say the ratio, the fraction of grams per meter matches the fraction of grams per meter because I've got a proportionality. I could set this problem up by saying, let's see, or I could shuffle this around. Say, let's see, mass 1 over mass 2 equals delta x1 over delta x2. Say that the stretch amount is proportional to the push amount. I've got 0.8 kilograms over 0.3 kilograms equals unknown kilogram, unknown stretch over 4 centimeters. 4 times 8/3 is 10.8 centimeters. We're going to be practicing setting up proportions and reasoning with ratios much more, especially next semester, even if I don't give you a number. Remember on the last test when I told you, if I apply 1 unit of force, I get 9 meters per second squared acceleration. What happens if I double the force? You can solve that besides just meditating upon what happens if I double this, what happens if I double that by setting up a ratio. More on that later. I wanted to highlight that as we're going to come. So again, here are the highlights, here are the takeaways for this on the screen. Spring constant doesn't vary. That's why it's called the constant. Find it once and use it again and again. Or set up proportional reasoning. If this increases, that must increase by the same amount. So if I multiply this by a factor of 4/3, 8/3, that must go by a factor of 8/3 as well. Yeah. Let's come back to this. Let's come back to this one. Okay. It's in the slides and I forgot it from last year. The answer to the question that he asked earlier, the maximum length it can get, that's called the elastic limit. Hey, forgot the technical term, but there it is. Okay, so vocab term, this is, if I recall correctly, this is occasionally used on, I'm not testing you on this term, but if I recall correctly, MCAT does ask a lot of things about exceeding the elastic limit and what you get in the Hooke's law region, in the elastic region versus not. So this is actually worthwhile to know for you future doctors. The elastic limit is the point at which a spring does not return to its original shape. That is where Hooke's law stops being applicable. I want to emphasize, just like we were saying before, if you stretch past the so-called elastic limit, the spring no longer returns to its original shape. You have stretched it out. It might pull back a little bit, but it's not returning to its, it won't look like it did when it started. Outside of the elastic region, you cannot use Hooke's law. Well, you can, but you get it wrong. Okay, here we go. Last thing. The last thing, the other equation you need to know is that spring constant. Well, I just presented it as if it's a constant that you have to find by knowing a force and knowing a stretch. If you know the force that a spring exerts and the length, or rather extension and length of the spring, bam, you can calculate its spring constant. But you can also predict the spring constant. There is an equation. There's an equation that pops up. This is not so applicable for next term, but this is huge for MCAT. And I do test on this so that not all of you will ignore, so that all of you won't ignore. And that is Young's modulus. Young's modulus allows us to predict spring constant for a given spring. In a sense, spring constant depends on what? Spring constant depends on the material. If you make a spring out of iron versus a steel versus a rubber, the spring's going to behave very differently, right? Well, Young's modulus says that the difference in the materials and the difference in the size and shape of the spring are ultimately what causes the different spring constants. Spring constant depends on size, shape, and material. Young's modulus is truly a material constant. You can just look it up. It probably changes with the temperature, but other than that, it's just tabulated. And here we go. I'm going to define Young's modulus in a second. But to do so, here are two terms to write this more neatly. Also, doctors, they ask you about this a lot. Stress is not just called physics homework. Thank you. You get A's. Stress, and to signify stress, we're going to signify stress. This is the Greek character sigma. Signify with signify with sigma. It's not just a boy, sigma, sigma boy. Is that how that goes? My son says it. What does it even mean? Oh, it's a song.
Yeah.
Oh, okay. He just says sigma boy, sigma boy, sigma boy, sigma boy, sigma boy, 6, 7 all the time. Anyway. So stress symbolized with the Greek letter sigma. This is lowercase sigma. The uppercase is the one that looks like an E. This is the ratio of force to cross-sectional area, force per area. This is the same, incidentally, as pressure. We're not going into pressure. I put a lot of pressure on you, but we're not going to study the physics of pressure. Pressure is a force per area, so is stress. Force per cross-sectional area of the spring. Strain, this is the Greek letter epsilon, right? It is a curly E. Strain is the ratio of stretch to length. That is to say, the proportional stretch. If you got a 5-centimeter spring that's 10 centimeters currently, your stretch is 100%, right? You have extended its length by 100%. Your change in length from 5 to 10 centimeters is 5 centimeters. Its original length is 5 centimeters, right? You know, strain is sale price, right? Oh, this coat is 95% of its original. Well, no, we don't say 95% of its original value. You say 5% off, right? Not like anything's on sale these days. 5% off, 95% of its original value. If you've got a 100-centimeter spring that's currently 95 centimeters long, it has lost 5% of its length. So strain would be 0.95 in that case. Proportional change in length. Note strain is unitless, by the way. Strain has no units, length per length. Sigma has units of newtons per square meter. Okay, so if we take these secondary terms, stress and strain, Young's modulus, Y, has the very, very simple formula of constant, true materials constant. Just look it up in a table. Iron is, I don't have these memorized, but iron is some number, equals the stress of that iron material bar, blah, over the strain of that iron material bar. Over that, yeah, I said that right. Okay, well, let's look inside this. If we restore sigma and epsilon to their if we restore sigma and epsilon to their defining equations above, I've got force per area divided by change in length per length, yeah? What happens if I've got a fraction inside a fraction? I can get the downstairs to simplify by multiplying both top and bottom by L over delta L. What do I get? FL over A delta L? Please tell me I did this right. I had a mistake last year, and then I think that I fixed it. Let's find out. So I've got a constant equals FL over A delta L. Hey, what's L mean again, by the way? What does L, as I just described it before? The length. The what length? The original length, the unstretched length. Okay, if I multiply these out, what do I get? YA y'all equals FL. Actually, I want to solve for F. The force exerted by the material is 3 constants multiplying together times the change in length. Oh my sweet baby Newton. Look, this is the spring equation. You see it? I haven't given you 2 equations today. I've given you 1 equation where I've gone inside what K is. This stuff is the insides of the spring constant K. Now, if I give you a given piece of springy material, do you have to ask me, what's the Young's modulus? Get out your calipers, measure its cross-sectional area? No, you just stretch it by a centimeter, find out the force it exerts, divide, and you get the spring constant. But, if you want to know where that comes from, we could reason about spring constant equals true materials constant times cross-section divided by unstretched length. You should know this connection, by the way, or be able to get this connection by writing down the terms. Spring constant is a true constant times the cross-section divided by the unstretched length. Yeah? You saw the pieces in play? Please. So in the original equation, I had the Young's modulus constant y is FL over A delta L. When I solved this for F, I got A delta L upstairs and L downstairs. A delta L upstairs, L downstairs, yeah? Delta L is the change in length. That's delta X. That's what I describe usually as delta X. So YA and L, YA are upstairs, L is downstairs inside K. Yup! Thank you. Wrong. Thank you. I remembered there being a typo. I was thinking it through, look for the typo, and my eyes glazed right over it. Thank you. This is not a correct equation. There is a typo on the original slide. K is not YL over A, K is YA over L. And you can check my algebra by looking inside this and solving for F. Did I do it right? Does this algebra hold? Check it for yourselves. Solve this expression for F. And you get A upstairs or A downstairs when you solve this for F. Google form B. Practice your algebra. If I solve this expression for F, do I get A upstairs or A downstairs in the final expression? Thank you. And Google form B is I want you to practice your algebra. And when you solve that equation for F, does A appear upstairs or downstairs? Oh, 50-50 response rate. Okay, so on average, if half of y'all are saying one thing and half of y'all are the other, that tells me that this is worth doing. Next. I want a new page. There we go. So our proposal here, not our proposal, our the pieces that we are connecting are that Young's modulus equals stress over strain. Stress is defined as force per area. Strain is defined as change in length per length. I want to algebra this a little bit. Maybe it was wrong to deal with a fraction inside a fraction. Let's multiply both sides by strain, shall we? In that case, I have force over cross-section equals Young's modulus times strain. Is this a legal step? Have I done this legally? Did I break something here? Great. Now, how do I get F alone? What do I do to both sides to get force on its own? Multiply by what? That's right. If I multiply left and I multiply right by A, okay, does A go upstairs or downstairs in the final force equals blah times tangent length? This is an upstairs, okay? Feel comfortable with this? Okay, so TLDR, if you weren't paying attention, one, stop not paying attention. Two, if you weren't paying attention, how did you hear me say pay attention? K is not YL over A, K is YA over L. Young's modulus times cross-sectional area divided by length. And let's move on. Here is a graph of stress versus strain. Now, if I define Young's modulus constant equals stress over strain, and then I graph stress on the vertical axis and strain on the horizontal axis, stress is nothing but y, strain is nothing but x. What slope? Rise over run, stress divided by strain, that's Young's modulus. If you have a graph of stress over strain for a material, then the Young's modulus is the slope of the line. Now, as you see here, this is not, in fact, a straight linear equation. But when I am not putting that much strain on the material, when I am not straining it that much, the graph starts out linearish. This is the so-called elastic region in here. Then we reach the elastic limit, and then funky bunch crap starts happening. This, if this is a bone, is where we call the bone fractures. This is actually a breaking. There's damage in this region. This is actually a snappy. At least, so the medical doctors tell me. There's all sorts of interesting stuff going on inside here, by the way. I have not studied this in detail, but I have heard the rumor on the street that the physics behind what's going on molecularly, biology and chemists probably know or would be able to read more about this than I do. I don't have the biology background to do it. But from what I understand, there's a lot of interesting stuff happening between cells and molecular bonds and inside materials. The chemistry of that, I believe, I have heard, is kind of cool. As I said, though, what we're going to stick for in the problems I'm going to give you is we're not going to be tangling with the entire graph all at once. Let's just start with the simple part. Well, we're just going to do the simple part in one day. Okay, do a problem. Do another problem. Oh, there it copied. What? What? Delete. What? Delete. Here we go. Let's talk about some spooters. I love spooters, except when they're near me. Or anything, really. But spooters! Solve for spooter silk. I give you Young's modulus. I give you problems. Please note, 0.155 millimeters is not an area. Hint, hint. This is Google Form C. This will be a couple of steps work together. Please note also 0.15 millimeters is not an area. It's also not a radius. I'm going to go fix the typo. Repost the slides. I just fixed the slides online. If you download or re-download, it will no longer have the YL over A typo. It will now be the correct YA over L. Sent myself to. Oh, I closed your side. For the person who asked, what does A stand for again? Area. A lot of people got the first part right. There are a lot of 10 to this off. A lot of people got 1.7 or 1.6 something. But then there are a lot of different powers. Let me address this and say that this is why scientific notation was invented. Here's a technique that I strongly encourage when you get an equation with lots of pieces put together. I do the equation by writing all the terms out and then processing the times 10 to the parts separately. So I've got a 4.9 10 to the third over 2 10 to the ninth, 1.77 10 to the negative eighth, 1.2 10 to the negative 1. I pull all the 10 to those out. I turn this into 4.9 times 1.2, dividing by the downstairs, over 2 times 1.77, and then I process all of the exponents. 10 to the, there's a minus 3 up here, so that turns into 10 to the minus 3. If I have a 10 to the 9 downstairs, that's a minus 9 from the exponent. Minus a negative 8 adds 8. Minus a negative 1 becomes minus 1 again. So I process all those separately, and I turn this into all the, I think they're called mantisses, all the part before the 10 to this separately, 4.9, 1.2, 2, 1.77, and then all of the exponents separately. 10 to the negative 3 minus 9 plus 8 minus 1 turns into 1.7, 10 to the minus 5 meters. Any equivalent version of this would receive full credit, 17 micrometers, 0.017 millimeters, whatever. You can express this in parsecs if you wish, although that's thoroughly silly. Maybe that would receive extra credit given that I like silly things. Okay, so that's really the big mistake I'm seeing with like half of the mistakes in here. A huge number of people got the 1.7 correct. You're missing the 10 to the power. Be careful. You should do a sanity check in here. I had a number of people say that it's like 10 to the 5 meters. 10 to the 5 meters is the size of a city, a big city, rather than look for ways to get an estimate, a feeling for how big things are, and you'll make fewer goofs. 10 to the 7 meters, that's the size of a planet, not a spider stretch. How do you feel about this stuff? Is this good? There's not much here. Hopefully this is relatively easy squeezy. Turn to your neighbor and discuss. I want one question, and then I think we're going to give you a quick preview on energy, and then we might even go early. But I do want one good question. Turn to your neighbor and discuss for 2 seconds.
Oh,
¿Tienes una pregunta? Which part? The radius? What's a diameter? What's diameter? What does it mean? What's a diameter and what's r in pi r squared? I mean, they're both about a circle. Radius and diameter are different terms. Can you define diameter? That's the circumference. Diameter is the full width of the circle. Radius is from the center to the edge of the circle. Yeah.
I got it. So you have
That's radius versus diameter. Well, radius is half of diameter. Then the formula for area for a circle is pi r squared, yeah. Vocab. There's additional stuff to learn, Finn. Good. Don't forget this, or revisit those. Okay, question me, question me. I hunger for your questions. Give me a question. We're not going deep on this stuff. Are you happy here? Do you know it? Don't clap your hands. Okay, great. Let's get a brief introduction to energy. Here is the topic for the rest of the semester. As I said before, energy ties in with like everything. It is the concept for your entirety of your bio, your chem, your biochem, your OChem, your everything. Aren't you always talking about calories and joules and stuff in them their classes, right? I haven't taken OChem and biochem, but I hear a lot of students complaining about them, and I peek over shoulders to see homework, and it's always got this stuff on, right? Tell me, you guys don't care about newtons in biochemistry class, do you? Right? But you are talking about joules all the time, free energy, kilocalories, blah, 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 blah. Okay, so here is my take on the top level view of what is energy. There are two kinds of energy. There is physics energy, and there's let's sell stuff to people energy. They are different. Sometimes they overlap, but they are different. Sell stuff to people energy can be found in spades if you go to the wonderful town of Sedona and look in the wonderful little shops. There are lots of things that will promise you much energy if only you buy them. And I can tell you that as a metaphor for emotion, as something to inspire you to give meaning to your life, if that's the sort of thing that gives meaning to your life, sure, go for it. But please distinguish carefully. Metaphysical energy, spiritual, emotional, artistic energy is not physics energy unless it can be caused to exert force over a distance. That's the acid test. It might possibly be a form of physics energy if you can conceivably get it to lift something. Energy has lots of different forms, and you can shuffle, you can transform it from one form to the other, and you can transfer it from one object to the other. But the acid test, the ultimate check, is can you cause, I guess you could express this in multiple ways, but can you get this to pick something up? For instance, gravitational energy is a form of energy we're going to talk about extensively. Gravitational energy is a form of energy because I can take, well, wait, hold on, that's the original, that's what I'm comparing everything to. Up, down position of an object is gravitational energy, is directly related to how hard gravity is pushing it up and down. And if you're able to push it up, or if gravity is able to pull it down, yes, there is a transformation of energy. So gravitational energy, check. Electrical energy, I have a battery. It has physics energy because I can use it to power an elevator, which lifts something up. If I can cause it to lift something up, that's physics energy. I can talk about, what else can I talk about? Energy. I could talk about energy in sound. If you have sound, which is captured by a microphone could convert sound energy into electrical energy. That's what a microphone is. I could theoretically shout long enough into a microphone to charge a battery to lift something up. There are actually radios, ham radios, that do that. You can send Morse code dots and dashes by literally shouting into the microphone, which I find absolutely hilarious. I haven't built it yet, but one of these days I'm going to. Ultimate de-stressor, yeah. Especially after finals, I get my students to send Morse code by shouting. Okay, anyway. So what else is a form of energy? Give me another form of energy. Heat energy. Heat energy. There's one I could think of. Heat energy is a form of energy. Enough heat, you can boil water to spin a turbine to power an engine to lift something against gravity. Muscles. I have food energy. I just ate a burrito. I actually have food energy for once. I have the food energy that I can use to power me lifting something up. Motion energy. I could take a ramp and have something that's moving along, go up the ramp, and then fly up into the air. That is, again, a form of energy. We're going to be talking about lots of forms of energy. We're going to be calculating with a few forms of energy. Hey, hold on a second. I've still got 7 minutes. We're going to be talking about a lot of form of energy. We're going to be calculating with a few of those. And in all of them, I want you to know, first off, the distinction between physics energy and metaphysical energy. And I want you to know what I just said before about energy can transform or transfer. I'm going to define this as transform means goes from one form to another. Duh. Transfer of energy goes from one object to another. Deep and powerful principle of energy, the topic of energy in physics, is that energy can go from one form to another. Energy can go from one object to another. But nothing that we will discuss in this class or next semester can ever change the total amount of energy. If you count up all the different forms and all the objects that are having 8 joules of energy, then later you found out that 7 joules of energy are left in the system, then that system must have put that 1 joule, expended it on some external object. There must be a transfer out of the system. The total what starts and the total what ends have to be balanced, or else that energy went into some third object somewhere else. Total amount of energy in the universe, theoretically, is constant. I'm lying to you, actually. There are ways to get around this. I have done this in the laboratory myself, but that's beyond the scope of this class. It requires either radiation, a particle accelerator, or a star. So you're not likely to need it. This is very common. You can create matter. Conservation of mass is also a lie. Details. Now I am done. Now you may leave. Adios, everyone.